Hey everyone, let's learn about Newton's method, which can be found in section 4.8 of Stewart. Newton's method is an application of the derivative, a nice little approximation technique that can be iterated multiple times, so it works very well, in particular with computers. Speaking of computers, find a decimal approximation to the square root of 3, let's say on a calculator, right? Well, we can go to Desmos, and we can type in the square root of 3. And it gives us this pretty good approximation, right? 1.732, let's say. Let's just use the first few digits, right? Now, let's go a little bit more. Let's see how go. 05080 757. Right, and that's an approximation, a very good approximation. It's still an approximation, right? Goes on forever, not repeating, irrational. Now, one thing you might be wondering is, how does the calculator approximate that? Well, it's possible that it uses an extended version of linear approximation called the Taylor series or Maclaurin series, but it's also likely, in this case especially, that it uses an algorithm estimation technique called Newton's method that we will learn. Before we go further, just recall that the zero, or we call it a root sometimes, of a function is a value a such that f of a equals 0. For example, we want to find all the zeros of this function right here. So one thing we can know from the fundamental theorem of, I think it's arithmetic, I think it is that all possible roots of this polynomial have to be factors of 6. So plus minus 1, plus minus 2, plus minus 3, or plus minus 6. Otherwise, it's something really messy, right? So it turns out that you can plug 1 in, and you get 1 cubed minus 7 times 1 plus 6, which equals 0. You can plug 2 in. You'll get 2 cubed. That's 8. Minus 14 plus 6. Also 0. Last but not least, you can try 3. It won't quite work, but negative 3 will. Negative 27 plus 21 plus 6 equals 0. So f of x, which, by the way, can be written as x minus 1 times x minus 2 times x plus 3, has roots, or maybe we'll call them zeros in this case. X equals 1, 2, and negative 3. Okay, quick little example. Here's Newton's method, which again approximates the zero of a polynomial, right? Those were really nice zeros. What if we didn't have such nice zeros? What if our zeros were irrational? Here's what you do. If you want to estimate a zero a, that's not such a nice value, then find an x value, x1, that is close to a. Ideally as close as possible. Maybe I should say is nice and also close to a, nice, like a whole number or something like that, right? Okay, then you want to find the value where the linear approximation at x1 equals 0 and call it x2. So remember that the linearization of a function is L of x equals f of, so normally it's f of a, but in this case a is our root, so we call this f of x1 plus f prime of x1 times x minus x1. We find x2 such that L of x2, in other words, that's this guy, but then we plug in x2 for x equals 0, okay? I.e., well, if you solve out for x2, right, subtract f of x1, divide by f prime of x1, and then add x1 to the other side, and you get that x2 equals x1 minus f of x1 divided by f prime of x1. Okay, that's the formula. Wash, rinse, and repeat, right? You just keep doing this. And then, of course, you replace x1 with x2, and, of course, the new 0 will be replaced, x2 will be replaced with x3. And then you do the same thing, replace x2 with x3, x3 with x4, and you just keep doing this until you get as close as you want. You want a better approximation? Just keep iterating Newton's method. So, let's use Newton's method to approximate root 3. I say as well as the calculator. It gave us a lot of terms. Maybe, I'm not sure if we'll be able to do so many of that by hand, but let's see what we can do. So for starters, we're going to let f of x equal x squared minus 3, because we have to recognize that root 3 is the 0 of this polynomial, right? And put that in parentheses, since f of root 3 equals 0. So, of course, let's just have this prepared since this is going to be in our formula. Note that f prime of x is going to equal 2x, okay? So, use Newton's method. We'll let x1 equal a value close to the square root of 3. Square root of 3 we saw was like 1.7 or so I think 2 is our best option. Okay? So that means that x2 is going to equal x1 minus f of x1 all over f prime of x1. Okay? And I think we can simplify this out a little bit more. This is 2 minus, well, f of 2 equals 1 fourth. This is 7/4. We'll probably use this to plug stuff back in. But it also equals 1.75. Already not a bad approximation. Right? We know the real answer is 1.73. Okay? So we're already reasonable. Now, we can just keep doing this, right? Replace x1 with x2, x2 with x3. So x3 is going to equal 1.75 minus f of 1.75 over f prime of 1.75. And by the way, how are you going to do this? Well, I think it might be easier to use fractions in this case. I'll just do this out, right? It's 7/4 minus, okay, f of 7/4, right? 49/16 when you square it minus 3, which is 48/16, gives you 1/16 up here. And then f prime of 7/4 is going to be 7/2. Reduce that, you get 1/56. So you have 7/4 minus 1/56, or 98/56 minus 1/56. So you wind up getting 97/56. Okay, so not the nicest looking thing in the world, but I'm approximating the square root of 3. It's not supposed to look all that nice. And maybe it seems kind of silly to use a calculator to approximate, but we're still going to do this just because we want to see how close we can get. 97/56, 1.7321. Right, and so this is the value where we're off by. So surely if we iterated it again, that 1 would probably turn into a 0. We would be good to go. Okay. I was going to say we could keep going. But as you see, it would be more and more complicated, right? Because we're using just messier and messier numbers. We could get an answer, but it wouldn't be simplified. Okay? And that's sort of the point. So let's just be clear about what we're doing with Newton's method. Remember that x2 equals x1 minus f of x1 divided by f prime of x1. x3 equals x2 minus f of x2 over f prime of x2. And in general, xn equals xn minus 1 minus f of xn minus 1 over f prime of xn minus 1. I got to be honest, I don't remember the formula very well. I always remember it as, look, take the linearization of xn minus 1, set it equal to 0, solve for xn. Plug xn in for x, solve for xn. Let me quickly illustrate what's going on here. Consider the function f of x equals x squared minus 3. Let's get rid of these guys, okay? What we've done is I've created the linearization and everything. By using Newton's method, we let x1 equal 2, and we found the linearization at 2, right? See, that's the tangent line, 2. And then we find where it equals 0. 1.5 comma 0, right? Just as we had found. Then we did it again. We found the next linearization, right? The linearization at 1.75, right? So it's tangent right there, right at 1.75, right above 1.750, okay? Then we found the 0 of that line, which is extremely close to the parabola, by the way. Right, 1.732 and some change, right? Now, if we had done it a third time, look how close we would have gotten. Oh my goodness, it's really difficult to find the parabola separated from that black line. Look how closely I have to zoom in. We're talking 100 millions here. Okay? And then just to be clear, these are the points that we're left with, right? Let me label these points just so you can see how close we get. A little bit further. And, no, I think I missed the green one right there. Okay, so you see the green one, 1.750. Purple one, 1.7321. But again, that's not the best approximation. Much better approximation is 1.73210. And let's just compare that to the coordinate root 3 comma 0. Right? It appears to be right on top of the black point, right? They're not quite the same, but the point is that doing this even 3 times, one more than we did, was a very good approximation. Okay? So what's Newton's method really? Well, given a function f of x with 0a, we let x1 be a nice value close to a, and find xn, which equals xn minus 1 minus minus f of xn minus 1 over f prime of xn minus 1. Okay. One quick example here, the value of x1 matters, right? Consider this curve, right? Cube root of x equals 0 for any x1 not equal to 0. Now, if this is a little ridiculous, we know that the cube root of x equals 0 has solution 0. But if you try any value that's not 0, look what happens. I don't know, let x1 equal 1. Okay? Actually, first off, let me write over here, let f of x equal the polynomial such that this is true. Well, that you just cube both sides. You're going to get, I guess, what is this? The cube root of x equals 0. So I guess we'll get the cube root of x. Yeah, I guess we'll just let it equal the cube root of x. right? There you go. Cube root of x. Okay? Let x1 equal 0. So I guess we're not doing polynomial, right? We're just letting f of x equal this, okay? So let's see what happens here. Well, x2 is going to equal 1 minus... Actually, sorry, let me just take f prime first really quickly. So f prime of x equals 1 over 3 cube root of x squared. Okay, just to be clear. Okay, so x2 equals 1 minus, this is going to be 1 over 1/3, which is 1 minus 3, which is negative 2. Okay, so x3 equals negative 2 minus f of negative 2, which remember that does exist, cube root of negative 2, divided by 1 over 3 times the cube root of negative 2 squared. Well, hold on a second. Cube root of negative 2 squared times the cube root of negative 2 is negative 2. This is negative 2 plus, let's see. Looks like it's 2/3. I was like, is that quite right? I feel like I messed something up there. A little bit there. It's supposed to be a little crazier than that. Hold on one sec. Let's let's make sure we did this right. All right, we're getting 2 minus... Oh, I see. Oh, no. See, I forgot to put the 3 up. Right, the 3 comes up also. So it's actually plus 6... Sorry, so what's happening? It's minus 3 times negative 2 over 1, which is 4. Or sorry, no, that's negative 2 times that's 4. Okay? So wait, we went from negative 2 to 4. One more. x4 equals... Any guesses here? 4 minus f of 4, cube root of 4, right, divided by f prime, cube root of 4. Right, that's that. So you're going to wind up getting 4 minus 3 times 4. I'll just put it down here, which is negative 8. This is obviously bad, right? Because we're getting further and further away from our answer of 0. Let's see really quickly why this happens. If this is our curve, y equals the cube root of x, if we start at any value that's not 0, well, if we do the tangent line, looks like that's where it's 0. And then we go up here. Find that line. Well, that's going to give us a point even further out. And then we go here. That's going to give us a line with a 0 even further out. So we're getting further and further away from our goal of the origin, right, 0, just because this curve is kind of weird. Okay, so be a little careful. Okay, another example of a failed Newton's method. Now, I pulled this one from Stewart. Approximate the root of this equation by first choosing x1 equals 1. Okay. So x2 is going to equal 1 minus f of 1. That shouldn't be too bad. 1 minus 3 plus 6, that's what, 4? Over f prime of 1, which is... Let's see the problem. 1 minus 4 over 3 times 1 squared minus 3. Why did this method fail? Right? This is 0. The tangent line is horizontal. Right? if we ever have a curve, right, let's actually take a look at this in Desmos, right? If we ever have a curve, we'll just get a new graph out here, where we have, let's see, horizontal tangent line, is that minus 3x plus 6, I think it was, right? So if we used 1, look at that tangent line. Or sorry, y equals 4, I meant to say, right? It's tangent, right? The tangent line at 1 is 0, or has slope 0, rather. Okay, so that's no good. So what should we do? We probably should, looking at this graph, we probably should have chosen a number like -2, or something like that, okay? And I will leave that to you to do Newton's method a couple of times until you get it correct to 2 places.